Hi, in this video we'll talk about absolute value functions. What an absolute value function does is it takes an input, x, and for the absolute value bars, what it does here is if your input is negative, it multiplies it by -1, making it positive, and if it's already non-negative, it just leaves it alone. So it operates in two very different ways. So we see that if the input is greater than or equal to 0, then we're just going to output x as though nothing had happened, as though the absolute value bars weren't even there. However, if your input is negative, then we're going to multiply that input by -1. Okay? Of course, what's inside our absolute value bars is not always going to be just simply x. Now, numerically, what this looks like is, for instance, if you have the absolute value of 4, that's a non-negative number, so it's just 4. Whereas if you have the absolute value of -1.7, it'll multiply that by -1 and give us positive 1.7. So the output is always going to be greater than or equal to 0. Of course, that talks about our range, and we can draw the graph of our function. So this is one of your prototypes. You can put it on your blue sheet after you've drawn it here. Now, if we're going to draw the graph of y equals the absolute value of x, if x is non-negative, that is, it's over to the right of the y-axis, then it just is the exact same as the line y equals x, because the absolute value bars aren't doing anything. So there's y equals x. However, if x is negative, then it acts like y equals -x, the line that looks like that. And those two pieces together, it's a nice continuous function, make up the graph of y equals the absolute value of x. So we see here that the domain is all real numbers. The range is from 0 to infinity, including the absolute value of 0 is 0. The y-intercept is at the origin, same as the x-intercept. And for asymptotes, there are none. But it has this strange point at the origin where the behavior of the graph switches radically. Okay? And you will study that sort of point in your further calculus courses. It's called a cusp. The function is continuous there, it's not broken at all, but the behavior changes radically. Now let's look at how to solve absolute value equations. And our technique is going to be based on this fundamental idea here, that if x is greater than or equal to 0, then our absolute value bars just act like brackets, and if the x value or the input is negative, then the absolute value bars act like brackets with a multiplier of -1 out front. So for instance, this equation here, we're going to break it into two cases. So in case 1, I'll switch colors here. In case 1, the absolute value bars are just acting like brackets. So I just replace them with brackets. Now these brackets, there's nothing outside of them, so I can just let them drop. There's nothing to distribute. And I have a nice linear equation that I can go ahead and solve. There we go. On the other hand, perhaps those absolute value bars are acting like brackets with a multiplier of -1 out front, switching the sign of what's inside. Well, in that case, I can distribute that multiplier of -1 out front inside. And again, I've got a nice linear equation that I can solve, but I'll get a different solution this time. Okay. So we see there are two different options. Now, of course, these are not necessarily solutions. We, of course, have to check. We are going to check in the original equation, because that's what we're trying to find, are solutions to that original equation. Now, if we take q equals -1, if I plug it into the left-hand side there, let's actually do a nice formal check at the bottom here. For the left-hand side, I get the absolute value of 3 times -1 minus 4. So that would be the absolute value of negative 7, which is 7. For the right-hand side, I would get 2 times negative 1 minus 5, which is negative 7. Okay, the left-hand side and the right-hand side are not the same. Therefore, q equals negative 1 is not a solution. Well, how about our other one? Maybe our other one works out. So again, we can try our formal check. We've got, for q equals 9/5, our left-hand side would be 3 times 9/5 minus 4, absolute value of that. So we'd have the absolute value of 27/5. Well, I want to write 4 as a certain number of fifths, so minus 20/5. And we get the absolute value of 7/5, which is 7/5. Okay. For the right-hand side, we get 2 times 9/5 minus 5. Well, that would be 18 over 5 minus 25 over 5, and we get negative 7/5. Okay? Again, that means that our candidate here does not pass the check. So, strangely enough here, this absolute value equation has no solution. Weird. All right. So, let's review our key tactic for solving absolute value equations. First thing you do is, in the first equation, the original equation, you're going to replace the absolute value bars with brackets and solve. Then you'll create a second equation where you'll replace the absolute value bars with brackets but with a factor of negative 1 out front. Of course, we'll have to distribute. And of course, we can never forget to check our solutions. Okay? And we check them in the original absolute value equation. All right, let's try a few more examples. All right, so we'll start off with a fairly simple one here. The absolute value of 3q minus 15 equals 0. So, we've got two cases. In the first case, the absolute value bars just act like brackets. Now, for those brackets there's nothing outside them. We can just let them drop. And we solve this nice linear equation. For case 2, the absolute value bars act like brackets, but with a multiplier of negative 1 out front. And again, we solve a nice linear equation here. Okay. So, we've got our two candidates here. If I plug q equals 5 into the left-hand side, I'll get, this whole thing is the left-hand side. I get the absolute value of 15, which is 15, minus 15, I get 0. That's the right-hand side. The first one checks. For case 2, q equals negative 5, plug it in, you get 3 times negative 5 is negative 15. Absolute value of that is positive 15. Minus 15 is in fact 0. Equals the right-hand side, it checks. Let's try another example. How about number 3 here? So again, our absolute value bars will just act like brackets. Here again, I can just let them drop. They're not serving any particular purpose. And solve that linear equation. Now for case 2, we'll think of the absolute value bars acting like brackets with a multiplier of negative 1 out front. Distribute in the negative 1. and solve that linear equation. And then, of course, we check them back in the original absolute value equation. Well, if we plug in 8, we get the absolute value of 16 plus 3, so that'd be the absolute value of 19, which is 19. That equals the right-hand side, which is 19. If we plug in negative 11, then we get negative 22 plus 3 is negative 19. The absolute value of that is positive 19. So they both check. Let's try another example here. How about number 5? So here again, we've got case 1. Our absolute value bars are just acting like brackets. We can drop those brackets because there's nothing out front of them. And we can solve this nice linear equation. Case 2. Our absolute value bars are acting like brackets, but with a multiplier of -1 out front. Distribute that -1 in. Solve the linear equation. And we get 2 candidates for solutions. Now, of course, we need to check them. Check here. Back in the original equation. If we plug in 5 halves, we get 25 halves minus 4, so minus 8 halves. That would give us 17 halves. Absolute value of that is 17 halves. That's our left-hand side. On the right-hand side, we get 15 halves plus 1, so plus 2 halves. That's 17 halves. Both the sides are equal. We have a solution there. For 3/8, if we plug it in, on the left-hand side, we get 15 eighths minus 32 eighths would be negative 17 eighths. The absolute value of that is positive 17 eighths. On the right-hand side, we get 3 times 3 eighths is 9 eighths, plus 1 plus 8 eighths would be 17 eighths. Again, we get the same value on both sides. That value checks as well. Now, I'll let you go back and try the other examples that we didn't get to. Okay? You'll find that exactly one of them has no solutions, and the other ones all have 2 solutions. So you can check those out for yourself. For the last example here, number 6, kind of a bonus question. Notice that there are 2 different expressions within our equation that have absolute value bars. What that means is we won't just have 2 cases, but we'll have more than 2 cases. I want you to think about that for a bit, and if you have any questions about it, come see me in my office. It's a good, challenging problem. Thank you.